All right, folks, so we're ready to have our conversation about the Krebs cycle. So before we do that, I want to let you know that sometimes the Krebs cycle is also referred to as the citric acid cycle. In fact, today you more often hear this, and sometimes the TCA cycle, which stands for tricarbolic acid. So let's just do a quick recap of where we've come from and that'll lead us up to where we need to be to understand today's note. So at the beginning of glycolysis, we started with a 6-carbon molecule of glucose. So here's our 6-carbon molecule. How many? 1, 2, 3, 4, 5, 6. Right? And the process of glycolysis enables us to split that 6-carbon molecule into 2 separate 3-carbon molecules, each called pyruvate. But through that process, we also end up creating some ATP, and we also end up making some NADH, those electron carriers that we talked about making use of later. Then we continued on in those 2 3-carbon molecules through pyruvate oxidation, ended up becoming 2 2-carbon molecules called acetyl coenzyme A. And so in that process, I end up making, pulling off a carbon off of each, so I end up with 2 CO2 molecules, but also another NADH per acetyl coenzyme A. So now I'm ready to continue to break down our carbon molecules. I still can break down these acetyl groups further and harness some of the energy held in the bonds and that chemical potential energy to maybe create some more ATP and some more electron carriers. And so that will lead us to the Krebs cycle, and that's where we are now. So the Krebs cycle or the citric acid cycle. All right, so I want to go through our note a little bit and discuss some important points. Okay, so what is the Krebs cycle? Well, it's a cycle, and so that implies that some particular piece of this process is going to happen over again. Okay, so it's cyclical. There's a particular molecule that is going to be recycled. And you've already seen the diagram of Krebs cycle, and so you can see that it is, in fact, cyclical. Okay, where is all this happening? Well, it's still happening in the mitochondrial matrix, right? And so we have our mitochondrion, and we have, there's my cristae. And so we've taken our 6-carbon glucose, broken it down. Pyruvate oxidation is sort of happening in the membrane, and then we're in the matrix now. This is where the events of the Krebs cycle are actually taking place. Okay, so as I mentioned before, we call it cyclical because this molecule oxaloacetate, which is produced at the very end of the Krebs cycle, ends up being the starting material when the cycle begins again. In other words, it becomes the reactant in step 1. And we'll take a look at that. Overall, here's where we are. So we end up with glucose having 6 carbons, 1, 2, 3, 4, 5, 6, broken down into 2 pyruvate molecules. That gives us the 2 acetyl coenzyme molecules and then the CO2s that came off when we oxidized pyruvate. So I still have those 6 carbon atoms, just organized a little bit differently, right? Now, where we're going with this in the Krebs cycle is we're going to further break apart these 2 acetyl coenzyme A groups to make more CO2. So here are the acetyl groups right here. Let me highlight that a little differently. Here are my acetyl groups. They're going to become, so this acetyl group right here is going to become 1, 2 carbon dioxides. And then the second acetyl group is going to become 2 more carbon dioxides. oxides. And then, of course, these guys are just the same CO2s as I had before. Okay, so that's how my accounting is going to work with my carbon atoms from beginning to end of the Krebs cycle. So you can see then that by the end of the Krebs cycle, all of the carbon that was in glucose here ends up as molecules of CO2. So no more of that glucose molecule is existing as part of a carbon chain anymore. They're all sort of moving around separately. So that's important to know. And we'll look at the specifics in a minute. All right, so now a couple of other things that I wanted to mention was that every time we break a carbon-carbon bond, there's a release of energy. And so the whole reason that we're breaking down glucose is to harness that energy and in the process trap it in some way. So the forms that we've seen it trapped as in previous steps of cellular respiration are as ATP and NADH. So in this case, in the citric acid cycle, in Krebs cycle, we're also going to see some of that energy used in producing some ATP, some small amounts of ATP via substrate level phosphorylation. But what we're also going to see is that we're going to produce some more electron carriers in the form of NADH and FADH2. Okay, so if we look at the overall equation, it looks a little daunting to begin with, but I think looking at it now, it will be, have a different impression than once we go through the Krebs cycle in its entirety, and then we look back at this. Okay, so one thing that's important to notice is that we start with oxaloacetate, but then we regenerate it in the end. Okay, so that's important to note, and that's what makes this a cycle. We're going to start with our acetyl coenzyme A. And what happens to that? Well, as we discussed, that ends up as molecules of CO2. Okay, so I get 2 CO2s for every acetyl coenzyme A, because acetyl coenzyme A, again, remember, is a 2-carbon compound. So this whole equation is actually just one turn of the cycle for one acetyl coenzyme A. Remember that I am starting this process with 2 acetyl coenzyme A, so that would require 2 turns of the Krebs cycle. Okay, so I'm going to start with an ADP, which means, and I'm going to phosphorylate it through the process of the Krebs cycle in order to produce an ATP. Looks like I have some electron carriers here that are going to be reduced in the process, and that will leave me with their reduced form as NADH and FADH2, which we're going to see again when we reach the section of the note on the electron transport chain. Okay, so as I mentioned before, we need to remember that since glycolysis is going to leave us with pyruvate, and then the pyruvate gets oxidized to 2 acetyl coenzyme A, that whole cycle is going to happen twice. And so we would have to double this equation in order to represent what would happen if we were starting with one whole glucose molecule. All right, so the CO2, of course, we know that that's a waste product. We expel that when we breathe out. And NADH and FADH2, our electron carriers, are going to move on to stage 4, the electron transport chain and chemiosmosis.